Hi, and welcome to a lecture on why classes, the argument for object-oriented programming. So our objective for this lecture isn't really about like technology or Python specifically. It's about a reason to give you for actually doing object-oriented programming, because everything we've done up until now is something called procedural programming, which is where we have like lists and dictionaries and we pass them to functions and we get data back and we do more stuff with data and data and functions. But there's another way to organize our code and our data and our functions, and that's with object-oriented programming. So I want to spend a little bit of time giving you a reason why OOP, that's what we call it, OOP, why OOP is better, quote unquote better, or what its advantages are over procedural programming, which is what we've done up until now. So let's talk about the problem that we face with procedural programming. So over here on the right, I've got a dictionary, which has a name in it, and then I pass it to a function named validate data, and then a function named enrich data, and then a function named normalize data. And then when I print it out, it's not only got the name in it now, but it's also got normalized and type. And the question is, where did all of that change? Where did those things get added to this dictionary? It had to have been inside one of these three functions here, but the question is where? Where are they? And so I would have to go and look at each of these function definitions and sort of like determine what's going on, and maybe, try to figure out where a bug is in one of those things. And maybe those functions are in different files and all over the place. So it becomes much harder for me to reason about like, where does change happen to my data? Because that's the whole point of a program. The whole point of a program is to have some data and change it in response to what a person is doing. If you're playing a video game, you're clicking on things to shoot them, that's changing the state of the game. Enemies are being exploded. If you're inside a really boring like tax application, like TurboTax, you're entering data and that's changing the state of your income tax return. And so the problem is how can we organize our code in a way that's more natural for the way that most people think, presumably the way that most people think. So let's talk about the problem a little more. So here we have a dictionary that describes some kind of car. It's a Mercedes-Benz GLS 450 and its current speed is 0. And then we pass that car to a function named accelerate. And then when we print out that car, we see that the value for speed is now 10. And so this is called procedural. This is procedural programming, where we take data like this and we pass it into functions like that. But in the real world, we don't do that. We have a thing like a car, and then we tell it to do something like accelerate. If I got into my car and then instead of pushing the car's gas pedal to accelerate it, if I had to take my car and give it to some function, I had to like put it in the shop just to accelerate it every time I wanted to speed up. That makes no sense, right? The ability for the acceleration of the car is built into the car. It's not just a piece of data. It's not just speed 0 here. It's the ability to have speed 0 and then tell the car, I want to accelerate. And then its speed gets bigger. So along those lines, the solution is we create these things called objects from classes, and we'll learn about all of this stuff in the upcoming lectures, I promise. But the idea here is that we can create a car. Look at this. We're creating a car and telling it, this is the GLS 450. And then that becomes a value that gets put into our variable car. And then rather than saying accelerate car, what we say is, hey, car, I want you to accelerate. And then when we print the car's speed, now it's bigger. So it's like we're flipping this stuff around. Instead of having a function and some data, and we take the data and pass it into the function, instead what we've got is our data and our functions all together inside something, and then we tell that thing what we want it to do. We want it to accelerate, and we want to be able to look at the speed of the car. This is what's known as object-oriented programming, because what I've got here is an object of type car. I've got a car object that's being stored in a variable named car. And so I'm interacting with this object. I'm doing car dot to do things with it. Car dot speed returns the speed. Car dot accelerate increases the speed. It's object-oriented rather than data-oriented. Like previously, we just had data and then we passed it around to functions. That's data-oriented. In this case, it's an object that has its own data inside of it, as well as its own functions that are special to that object. So now we're going to have to change the way that we think about the problems that we're solving. Instead of just identifying the data and the functions, what we want to do is we want to think about real world things. We want to think about things in the world, the ideas and objects and things like that. A tree, a car, a person. Those are real world things. An invoice, my credit card bill, a credit card transaction. All of those things are real things in the real world. These are known as real world things. And if I create classes, if I create things which model those, then that is modeling our program. So, previously on the previous slide, we saw that there was a car object which modeled a car. It is a car for the purposes of our program. It doesn't do everything that a car does. We can't actually climb into it and drive away, but for our program, the car itself, to have a model and what its current speed is, that is something that is important for our program and the real world things that are represented inside that program. So we're going to step through the whole, let's figure out what our problem domain is. So problem domain, what that is that's the thing that we're trying to solve, that we're trying to write software for. There is a problem out there in a domain. So for example, in oil and gas, for example, one of the things that we might want to model is like pipelines where oil flows through. And if we're at a bank, we would want to be able to model the problem of customers being able to put money in the bank and getting money out of the bank. And what kind of bank account do they have? Is it a checking account or a savings account? All of these things are part of a problem domain. And one size does not fit all. So if I have the idea of a car for a sales lot, okay, so the place where they're actually selling cars to you, those gross places where they're like, hey, buy me a car, that car idea would be different than, say, a car representation in a manufacturing plant, because you want to be able to track different things between these two. They're different problem domains, but they have similar concepts between them. So you can have separate problem domains with completely separate ideas that represent the same real world object. So let's take a look at this problem domain here. I'm going to give you a minute to just go ahead and read that paragraph. So you know how much I really hate examples that have to do with let's go to school. That's not the kind of thing that I like to do. But in this case here, we're gonna go with quizzes because because why not? We've been taking quizzes this entire class. So inside our brains, we kind of know how they work. In most textbooks, you're going to find them to be like, hey, find me the nouns in your problem domain, and that's going to be the ideas, the abstractions, the objects that you're going to want in there. Okay, so that's what most OOP textbooks say, and I'm going to say that's what we're going to learn right now. There are different ways to go about the whole modeling thing, but okay, so we're just going to stick with the whole noun identification thing. So inside this problem domain description we've got here, the nouns become the things in our system, and those things are the objects in object-oriented programming. So I've got them bolded over here. A quiz, that's a noun, and it's made up of true, false questions. So, that's a noun. And then multiple choice questions, that's a noun. And multiple choice question, well, that's a noun. That's just the other noun. And it has options, and those options are inside the multiple choice question. And then there were answers, right? Because, somebody has to actually give an answer, a response to this. So how many questions were answered correctly? So that's some sort of thing. And then, we've also got quiz here and, that sort of thing right there. So look at that right there. Here are the nouns inside our thing. So now that we've got the nouns, let's do a little bit of like ideation around those nouns. All right, so now that we have the nouns, our next step is to figure out if we can like simplify this list. So we've got, the quiz. That's going to be a real thing. That's a thing that we've got in true, false question and multiple choice question. But then we get to like answer to a question. What's that going to be? That's going to be somebody typing in like true or false or option A or option B or whatever. So that answer to a question here, this could really just be a string. This could just be something like a string that we capture from them, from the input function. So we don't need any like custom thing for this. We're just going to make that a string. Whereas a true false question is more than a string, right? A true false question is not only a string that contains like the question text, but also like what's the correct answer? Is it true or false? And the multiple choice question needs, it's not only the text for the question, but also all of the options that are inside it. So these are complex things. They're not just single things. And then here we have multiple choice question option. What's that? That's probably just a string as well. So because it's just a string, we don't need a custom thing for that. So what we've really got are three first-class complex ideas here. The quiz, which has, all of the questions and tells you whether or not they're right or wrong. The true-false question that determines, hey, what is the correct answer? Is this question true or false? And what is the text for the question? And then the multiple choice question. So here are the nouns for our custom things: the quiz, the true-false question, and the multiple choice question. All right, so after we figure out the nouns, we have to figure out the verbs for those nouns. So if we go back to the problem domain and we look at it, we have to figure out what it does. And the only thing that it says in there is that a quiz needs to report which questions were correct, or actually it just says how many were actually correctly answered. So for our quiz, we have a verb of like, let's get the score, okay? After we do the quiz, after a person takes the quiz, let's get the score from the quiz and put it out so that people are like, oh, I got 20 out of 25, or I got 3 out of 100, which is sort of how I feel like the midterm I just took. Oh my God, I took a midterm last week and it totally kicked my butt. Oh my goodness, it was a 3-hour midterm. It was only like 37 questions, but OMG, so hard. Anyway, get score. So that is a verb that we have for our quiz. We say, hey, quiz, give me the score. I want to get the score for somebody who just took that quiz. So that's a verb. It's the only verb that we really had in there. All right, so after we figure out what the verbs are that are listed, now we sort of have to figure out what the verbs are that are implied by it. So let's think about a true-false question. If I answer true, that question will know whether or not I'm right by my response. And if I have a multiple choice question and the options are A, B, C, and D, and I respond C, then that multiple choice question will know whether or not it's right or wrong because, when I created the question, I told it which was the right option. So in that case, now my question, both of these question objects have 2 implied verbs. And I'm just sort of like, I'm making these up as I go along just to like get a feel. If it feels right, it might be right. So when I have a question and somebody gives me a response, I want to set the response to that question, and then I can ask it if it's correct. And the same thing for multiple choice. I can set a response, and then I can get is correct. Back to the quiz. A quiz is a collection of questions, so I need to be able to add questions to it. So add question is a verb for my quiz. And then also administer, which is like run the quiz. It's like, hey, quiz, start up and start printing out the questions and collecting responses. That's quiz. Hey, I want to administer the quiz to the folks. So here are more verbs that we're hiding inside of it. And I want to point out something here. All of these things here, that like these 2 here, these implied ones, I just sort of like figured those out as I was thinking about the domain problem. Because the question is, how does this software work? What's a question know about? The question knows, the true false question knows, what is the text for the true false prompt? And then is it true or false? What's the correct answer? So that's a true false question. But, if I set the response on it, then I can also ask it, is that response correct? Did the person get that problem correct? And so I'm just sort of like feeling these kinds of things out. So we always come back to this. Why is this better? Why is this idea of object-oriented programming better? And people who like object-oriented programming, they're going to tell you a couple of things. They're going to say it reduces the cognitive overload, which just means we can think about the program more simply. If we have something, if we have an object, which represents the true-false question, then everything that has to do with the true-false question, its data, its functions, how they interact with each other, all of that is going to be bundled together. So when I think about a true-false question, I can just go look in one place and figure it out. And then according to proponents of object-oriented programming, it's also simpler to find bugs and add new features. And we'll see this in the lecture as I go along. I will be building an object-oriented quiz for us, and so we can see how that goes. It's important to note that we've already been using objects. Basically everything in Python is an object. And so here we're creating a list, L, from this list. And then this L.append is a method on that list, which allows us to add something to the list. The data, this is the data that's inside the list. And when I call L.append, it changes the data inside that list. That list is an object. It's got data inside it. And when I do L of 0 like this, that's another method that says, get me the 0 element, give me the index 0, the 0th element from here, and print that out. And here, L of -1 is a method which says, I want to set the value at the -1 index to whatever is here. And then also strings down here. Strings are also objects. Everything's an object. Functions are objects. Everything is an object. And so because this data is inside that string object, we can do things like ask that string object, is this a, is a digit? Is all of the characters inside here, is it a digit? And what the string object does, the string object itself looks inside there and is like, digit yes, digit yes, digit yes, digit yes, digit yes, digit yes, digit yes. Yes, it's all a digit, that kind of thing. Because the string object owns these characters inside of it. We can't go inside and mess around with crap. Instead, we have to go through the object and use its methods like isDigit, append, and then these square bracket accessors. Those are all methods underneath the covers that allow us to interact with the data that's inside the object. So again, let me recap why people think that OOP is better. There's lots of people who think that object-oriented programming is better. I was one of them for a really long time. I still think OOP is great. I mean, OOP is wonderful. OOP is a tool. OOP is just a way that we can do things in a language that supports object-oriented programming. There's nothing wrong with using it if we use it correctly. And so the proponents like me would say, hey, using object-oriented programming is a more natural way to think about the world. The stuff that we see in the world, we can model as classes, and we'll see that in the next lecture. We can turn those into classes that then define the objects that we'll be interacting with. Some people say that it's better code organization. You can actually go find places. Like if I want to look at a car class, I'll know where it is because all I've got to do is look at class car. I've got to go find it. So being able to figure out where the data and where the functions are and how they interact with one another, you go to basically one place. Again, easier to reason about the code because we can think about the objects as things. We can be like, that is a car object. And I know in this program, cars can drive and, they can honk at things. And so I can take all of that abstraction, that idea of a car, and package it up inside my head and be like, that's a car object. So it's easier to reason about the code. And then finally, because of all of those things, supposedly it's easier to maintain software. I have been in object-oriented systems, like really large software systems, programs, and let me tell you, once things get large, in my opinion, irrespective of how you're doing it, whether it's procedural programming or object-oriented programming or functional programming, big software is hard to maintain. One of the things that OOP allows us to do is be able to help carve out pieces so that we can think about it easier. So if there's a bug or a new feature that we want to add, we sort of know exactly where to go inside our code to go fix it. So easier to maintain the software. And so in our next lecture, I'm actually going to code this entire program domain. I'm going to show you how to write an interactive command line quiz where we will create true-false questions and multiple choice questions. We'll pop them into the quiz and, we'll just see if it works. Right now, I want to point out, I've got these verbs here on each of these objects. Once I start programming, this may change. Okay, it's really important to understand that this whole idea at the beginning of like breaking down your problem domain into things and the verbs on those things, they can change. Okay, as a matter of fact, it will most likely change. But the reason that we go through this entire process here is so that we can at least have a starting point when we start thinking about how these things are going to work together. So this may change. And when I say may, I'm going to write this will change, okay? There's going to be things that we're going to get to, and it's going to be like, maybe I want to do it differently, or maybe this is not the correct way to do it. So, this will change. And that's one of the things that we have to be, do as software developers. We have to embrace change because our programs will always change. There's no program out there that somebody wrote once, put out in the world, and then was like, I'm done. There were bugs to fix. There were new feature requests to add. If you work for a company, then they're like, we've got to grow our user base. We have to lower our customers' total cost of ownership of their software ecosystem. And we need a larger addressable market. That kind of total addressable market. Those people are always like, hey, we need more stuff in our software. And so because of that, things will change if you become a software developer. So you might as well just like lean back and be okay with it.